Hello, welcome back to another CHE 2511 Basic Organic Chemistry session with me, Jackson. And today we're going to look over ring strain. Yeah, ring strain. Basically, not the only thing, but it's something that I wanted to highlight. So, what do we actually mean when we talk about strain in organic chemistry? So, we are essentially looking at why some molecules are more stable compared to others. So, you can think of strain as internal stress or pressure. So, the more a molecule has, the more it wants to react or change shape to relieve that pressure. So, under ring strain, we discuss two important strains, that is angle strain, and we also look at torsional strain. So you have to be able to differentiate angle strain from torsional strain. And then we also look at another aspect or another type of strain, which is steric. It's not necessarily a ring strain, but we also look at steric hindrance. We often hear steric hindrance, but what is it in organic chemistry? So when you talk of angle strain is just a type of strain that occurs when the actual bond angles in the molecule are forced to deviate from their ideal bond angles. When they are forced to deviate from their ideal bond angles due to structure constraints, you know, there's nothing that a compound can do about it. So the structure constraints of that compound. For example, it can be attributed to rings. That's the major example that I can think of, rings. And as the name suggests, ring strain. So angle strain is a result of a deviation from the ideal bond angle. For example, the carbon atoms of alkanes are sp3 hybridized. So meaning the normal tetrahedral bond angle of an sp3 hybridized atom is 109.5 degrees. But we have molecules like cyclopropane. We have molecules like cyclopropane, like the shape of a triangle with bond angles at 60 degrees. So it means there's a deviation. Imagine from 109, this is the ideal bond angle, to 60 degrees. So that's like 109.5 minus 60, that's like negative 49.5. So it's a large amount to depart from. Imagine this is your ideal bond angle, and then you get this. So yeah, as a result of that, we have angle strain, because it seems like there's some structural constraint. There's no movement in these sigma bonds, and because of this structure, there's also no effective overlap. Because in normal alkanes, if you draw them like this, these orbitals, the pi orbitals, there's some overlap. But then in this ring type, there's no overlap. There's no perfect end on overlap, so it's not possible. How about torsional strain? So you have to be able to differentiate the angle strain from torsional strain. Torsional strain, on the other hand, is as a result of eclipsing, when atoms that are separated by three bonds are aligned in the one atom is aligned behind another atom. So it's more of the atoms that are separated by three bonds are forced into an eclipsed conformation. So this all happens because the sigma bond can rotate, and so different atoms find themselves in different positions. So we can think of torsional strain due to eclipsing. Eclipsing, let's say we put a carbon atom here, and we also have a carbon atom here. And let's say this carbon you're viewing it from, you're looking at, you're holding, let's see how I can explain it this simply. Let's say you have this carbon, and then this is another carbon at the back. And then this carbon at the back has a hydrogen, and this carbon at the back has a hydrogen. So if you're looking at it from this, if this is your eye, if you're looking at it from this angle, you will not be able to see the carbon at the back, but you can see this carbon and this hydrogen, and then separated by 3 bonds, 1, 2, 3. So if you're comparing this hydrogen and this hydrogen, if you're looking at it from the front, it's like you won't be able to see this hydrogen at the back. This hydrogen at the back has been eclipsed with this hydrogen. They are aligned in the same way, such that you are not able to see that hydrogen at the back. So that's basically it on torsional strain. And the visual representation of torsional strain will be Newman projection that we discuss in the next video. When front hydrogens sit directly in front of the back hydrogens, they're eclipsed, and so the torsional strain is at its peak. So for you to fix this type of strain, it's like you have to rotate the molecules around the sigma bond. We'll look further in that when we look at the Newman projections. Then the other type of strain is steric hindrance. What is steric hindrance? Steric strain, steric hindrance. So this occurs when non-bonded atoms or groups are just forced too close to each other, such that their electron clouds start to repel. Remember, like tend repel each other. So two bulky groups, the bulkiness is a factor. Two objects cannot occupy the same space at the same time. So it's like they're too close to each other, so they repel, the electron clouds repel each other. So again, the visual, to visualize this, we will look at Newman projections in the next video, but that's basically it on steric strain. So we've got a question that we need to tackle. Identify the types of strain that are present in angle. That's angle, torsional, or steric in each of the following compounds. We've got compound A, which is just 1 carbon, second carbon. This is like ethane. So what kind of strain are here? Is it a ring? Definitely no, it's not a ring. So we won't have angle strain. Angle strain is usually for ring like cyclopropane. Cyclopropane ring has angle strain, but for this one we have torsional strain because separated by 3 bonds. If I have this hydrogen here, 2, and if I have this hydrogen here, imagine if you're looking at it from this side, your eye is here, meaning you are able to see this carbon and you can't see this carbon at the back, and then hydrogen is in such a way that it's aligned in the same way with this hydrogen. It's at the back. So here it can have an eclipse conformation. So it can be eclipsed. It can rotate in such a way that this sigma bond can rotate in such a way that this hydrogen and this hydrogen are aligned together. Do we have steric strain? No, because we do not have bulky groups that are on this carbon and this carbon do not have bulky groups on each other. So size matters when it comes to steric strain, and hydrogen atoms are just too small and they rarely cause any significant steric strain. But groups like butyl, methyl groups, if they're close to each other, then the electron clouds can start to repel each other. So for this molecule, for this compound here, the strain that's present is simply torsional strain due to eclipsing. And then when we go on B, it's the same. It's a butane. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So it's a butane molecule. This compound is butane, and the way it's been drawn out, so we do not have angle strength, but we definitely have steric strain because of this group and this group, or this group and this group. If you're comparing the groups that are on different carbons, this group and this group, this is bulky and this is bulky, so we are bound to have some steric strain. Torsional strain again, because when this carbon, when I'm viewing from this carbon, the groups here can be arranged, the atoms here, hydrogen, hydrogen and metal group of this carbon can be arranged in such a way that they are eclipsed with this, this and this. So definitely here we also have some torsional strain. So here we definitely have torsional strain and some steric strain because of the bulky groups, looking at the way it has been written out. How about this C? Of course it's an angle. These the carbon atoms of alkanes are sp3 hybridized, so the ideal angle should be 109.5, but then this angle is 60 degrees. So of course, structure constraint, we have angle strain because this is 60 degrees, and also we do not have steric strain because these groups, the hydrogens, it's not significant, so I can just say it's negligible, but there is some kind of the strain is not significant, of course, the steric strain, because they're not bulky. How about the torsional strain? So while angle strain here accounts for the most ring strain in cyclopropane. Remember, ring strain is composed of angle strain and torsional strain. So while angle strain accounts for the most of the ring strain in cyclopropane, it does not account for it all because the ring is planar. The fact that it is planar, the CH bonds of the ring are all eclipsed. So if you look at this carbon here and this carbon here, if you're looking at it from this angle, you'll find that in such a way that this is your front carbon, you find that this hydrogen is eclipsed with this hydrogen because this is bond 1, 2, 3. Remember, torsional is as a result of atoms that are separated by 3 bonds, and these hydrogens are in such a way that they are eclipsed this hydrogen because of this molecule is also planar. So it means this molecule, this atom here, the hydrogen atom here, and this hydrogen atom here are eclipsed. Same this and this are eclipsed. This and this are eclipsed. Also this and this here are also in such a way that they are eclipsed. So here we have angle strain, and we also have torsional strain because of the eclipsing. So to understand what eclipsing is, in the next video we'll discuss Newman projections and how to draw them and how you're able to rotate the sigma bonds, because when a sigma bond is rotated, you're able to relieve some of the stress. You can either increase the stress or relieve, but naturally compounds would tend to relieve the stress. So the sigma bond will be rotated in such a way that the bond is relieved. So we'll look at ways in which the sigma bond will rotate in such a way that some of the strain is relieved.